In this video, we're going to do an example of a multi-loop circuit in which we know the voltage of all of the batteries and the resistance of all of the resistors. In the diagram, we have already labeled the direction of the currents that we are interested in. That is, we have I1, which is flowing in the red highlighted region. So everywhere where we have a red highlight, that current there is I1, and we are defining I1 to be positive, we are defining positive current as flowing in the clockwise direction in that region. The second region, this area that I've marked blue over to the right here, is where I2 is. And we define current I2 as being positive if it flows in the clockwise direction in the blue region. And lastly, we have the center region where I3 is flowing, and we define any current that is flowing downward in this green central region as being a positive current. Now, because we haven't actually solved mathematically for these currents yet, we have no indication that they are truly flowing in the way that these arrows point. This is not some mathematical manipulation that we have done where we actually know these currents are. We are defining a convention, like defining a coordinate system. And it may turn out that the current truly flows in the opposite direction of these blue arrows once we do the math out. But in order to solve that, we need some convention for what is positive current, and that's what the blue arrows are indicating. Our goal here is going to be to take 3 different loops of current and to use Kirchhoff's voltage rule around each of the loops. Kirchhoff's voltage rule says that the total voltage, the total change in voltage across any closed loop must equal 0. So our goal is going to be to traverse all of the loops that we can find in this circuit and set the total change in voltage around that loop equal to 0. So the 3 loops that we are going to look at are the loop on the left side, which moves around the left side of the circuit as shown here, and we are going to move in the direction where the currents flow. This just makes our life a little bit easier, as we will see. We could have chosen the loop to flow in the counterclockwise direction instead, and everything would have worked out fine in that case as well. The second loop that we're going to look at is the loop that goes around the full outside of the circuit. So we're going to add up the voltages for everything that we run into as we track around the full outside of the circuit. And the third loop that we're going to look at is a loop that goes around the right side of the circuit. So we're going to start with our red first loop, and then we'll move on from there. And what we're going to do is we are just going to add up each of the voltage gains or drops that we see as we move around the loop. Before we begin adding up our voltages around the loops, we can first look at Kirchhoff's current rule. We can see that if we look at point B, the current going into point B is I1, and the current going out of point B is I2 and I3. So using Kirchhoff's second law, we can say that I1 equals I2 plus I3. Let's begin by looking at the red loop on the left-hand side and adding up each of the voltage gains or drops, starting with the 18-volt battery. So as we move clockwise around the loop, we're moving from the negative side of the 18-volt battery to the positive side. And as you move from the negative to the positive side of a battery, you gain electric potential. So that is a positive 18 volts that we are gaining. The next thing that we can look at is this R1 resistor here. Now, this resistor, as we move across the resistor, we are going to lose voltage. So one way to think about this is if you have a normal, just single resistor circuit with some battery, let's say it's a 9-volt battery. So there's 9 volts on the positive end, there's 0 volts on the negative end, and we have some resistor in our circuit. We can note that in order for Kirchhoff's loop rule to work here, if we have a gain of 9 volts across the battery, that we must lose the same 9 volts across the resistor. So this side of the resistor is at 9 volts and this side of the resistor is at 0 volts. So Kirchhoff's loop rule for this system would be plus 9 volts minus 9 volts equals 0, right? So as I move across a resistor in the direction of the current flow, which in this case is clearly in the counterclockwise direction, flowing from the positive side of the battery to the negative side of the battery, our battery gains us voltage and our resistor loses us voltage. So when we move in the direction of current, our resistors have a voltage drop across them. So we can write the voltage drop across this 0.5 ohm resistor as minus 0.5 ohms multiplied by I1, because I1 is the current that is flowing through this left-hand side. Anywhere in the red shaded region has a current of I1. So we're going to lose some voltage. Note that this is simply a V equals IR, right? We're taking the current through that resistor, multiplying it by the resistance of that resistor. The next thing that we're going to do is we're going to get to our R1 resistor at the top of the diagram here, which is a 20 ohm resistor. We're again moving in the direction of our current, so that is going to be a voltage drop across that resistor. So we have minus 20 ohms multiplied by I1. We then turn down following our red loop there, and we run into a 6 ohm resistor. Again, we're moving in the direction of I3, so that's a subtracting 6 ohms multiplied by I3. And then we are going to arrive at a battery. Now, the battery is set up such that we are moving from the negative side of the battery at the top to the positive side, which means we are gaining voltage as we move across this battery. So we add 3 volts to our total voltage tally. We then arrive at R2, a 0.25 ohm resistor, and we subtract 0.25 ohms multiplied by I3. We then move left and get to the R4 resistor. The R4 resistor is a 15 ohm resistor with current I1 flowing through it because it's in our red shaded portion. So it has a current of I1. And this current is flowing in the clockwise direction, just like we are moving around our loop. So we lose a voltage of 15 ohms multiplied by I1. And the Kirchhoff voltage law tells us that the sum of all of these voltage gains and drops must be 0. Okay, So that is the voltage equation for our first loop, our red loop on the left here. The next thing that we're going to do is we are going to do the loop number 2, our blue loop moving around the outside. So for loop 2, we are again going to start at the 18 volt battery. To begin with, we write down the positive 18 volts that we gain by moving upwards through this battery. We then, just like for I1, arrive at our two resistors, the 0.5 ohm resistor and the 20 ohm resistor, both of which have current I1 flowing through them. So we have exactly the same terms as we did for loop 1 here. Next, we continue to the right and we reach R3, our 8 ohm resistor. And because our current is moving to the right in the same direction that we are traveling around the loop, we lose that 8 ohms multiplied by I2. So we have 8 ohms multiplied by I2. Then we hit the 12 volt battery, which is aligned such that we are moving from the negative end of the battery to the positive end of the battery, which means that we gain, sorry, I wrote that backwards there. We move from the negative end to the positive end, so we're gaining voltage. So we add 12 volts into our sum. We then hit 2 more resistors where we are going to lose voltage. So we have minus 0.5 ohms multiplied by I2 minus 0.75 ohms also multiplied by I2. We then hit a battery which is facing the other direction, which means that we end up moving from the positive end of the battery to the negative end. And when we do that, we are going to lose voltage. So we're going to lose 24 volts here as we move around, move across this E4 battery. And then finally, we're going to lose some more as we have our 15 ohm resistor with I1 passing through it over here just before we get back to our original point of the 18 volt battery. And when we add all of these things up again, it must equal 0. Now finally, we're going to look at the loop through the right side of this circuit. Starting at the 12 volts, we are going to move in a clockwise direction around, like so. So our voltage gain is going to be 12 volts from the battery because we are moving from the minus to the positive side of the battery. We're then going to lose voltage across the 2 resistors. In this region, we have I2 flowing, and so we have our resistance multiplied by I2 of 0.5 and 0.75. Next, we get to our battery, which is kind of put in backwards, such that we are moving from the positive to the negative side of this battery, which means we lose 24 volts of potential as we drop from the positive to the negative side. Then we're going to take a right at the fork at point E and move up through this 0.25. Now, here is the important point to note. We said that I3 is positive if it is moving downward. That was our convention at the beginning. And now we're moving the other way. We're moving up through this central pillar, which means that we are moving in the opposite direction of the current. So we are going to gain voltage as we do so, which means we add 0.25 ohms times I3. We move backwards through the battery. So we are moving from the positive to the negative side of the 3 volt battery in the center. So we subtract that off, And then we hit our 6 ohm resistor, which we are again moving the wrong way through. We're moving against the current. So we gain voltage as we move across it. So we get plus 6 ohms multiplied by I3. Finally, we take a right at point B here and we head over into the 8 ohm resistor, where we now start moving with the current again. We're moving with I2 and we get minus 8 ohms times I2. And then we're back where we started with our 12 volt battery. And the sum of all of these must be 0. So this is our loop 3 equation. So now we have 4 total equations and 3 unknowns. Our unknowns are our I1, I2, and I3. And our equations are the Kirchhoff loop rule for loop 1, loop 2, and loop 3. And we have the Kirchhoff rule for adding currents. And when we only have 3 unknowns, we only need 3 equations to solve for them. So it turns out that one of these equations is actually redundant in the loop equations. They actually give us the same information, and we could solve this problem with only 2 of the 3 loop equations. In order to show that these equations are in fact redundant, and that there are only 2 independent equations from our loop rule, the first thing that we're going to do is that we can simplify our 3 loop equations by combining terms with the same type of I. So for example, we can rewrite our first loop equation as 18 plus 3 volts is going to be 21 volts. Our I1 terms, we have 3 I1 terms here, which add up to a total of negative 35.5 ohms multiplied by 1 by I1. And we have 2 I3 terms, which add up to negative 6.25 ohms times I3. And that must equal 0. We can rewrite the second equation by combining terms. Our volts, we have 18 volts plus 12 volts minus 24 volts is going to be a total of 6 volts. Our I1 terms, we have, again, a total of negative 35.5 ohms multiplied by I1. And we have I2 terms adding up to 9.25 ohms multiplied by I2. And that also equals 0. Finally, we can do our third equation. Our voltages, we have plus 12 volts minus 3 volts minus 24 volts, which turns out to be minus 15 volts. We also have I2 terms, which total, just like in the last one, they're going to total negative 9.25 for our I2 terms. So we subtract 9.25 ohms times I2. And we have I3 terms, which are actually both positive. So we end up with plus 6.25 ohms multiplied by I3, and that also equals 0. Now, as a quick check, we can take equation 2, all of the terms of equation 2, and subtract equation 1 from it. So this gives us combining the first terms, negative 15 volts. That is 6 volts minus 21 volts is 15 volts. The second part, I have minus 35 ohms times I1, and then I'm going to subtract a negative 35.5, so that's 0 times I1. Then I have a minus 9.25 ohms times I2, and then I subtract a negative 6.25 ohms times I3, which turns into 15 volts minus 9.25 ohms I2 plus 6.25 ohms I3, which equals 0, and this is in fact equation 3. So this just proves that equation 2 and equation 1, when combined, give equation 3. This is called being not linearly independent. It means that equation 3 is simply a combination of equations 1 and 2. So in order to solve our problem to find our I1, I2, and I3, we need 3 independent equations. And the equations that we're going to choose are going to be equation 1, 2, and our current law equation. So what we're going to do is we're going to take our 2 simplified loop equations 1 and 2, and we're going to combine them with our current equation, I1 equals I2 plus I3, and we're going to try to solve those 3 equations together to find values for I1, I2, and I3. In order to solve these 2 equations, what I'm going to do is I'm going to take my current equation and I'm going to plug in I1 equals I2 plus I3 in both of these equations. So I could say that 21 volts minus 35.5 ohms multiplied by I2 plus I3 minus 6.25 ohms multiplied by I3 equals 0. And I'm going to do the same thing with my second equation, 6 volts minus 35.5 ohms multiplied by I2 plus I3 minus 9.25 ohms multiplied by I2 equals 0. So now what I can do is I can solve, for example, the bottom equation for I2 in terms of I3, and then I can plug that value for I2, or that expression for I2, into the top equation, and I can get an equation that depends only on I3. So let's try it. What we're going to do is we are going to solve this bottom equation for I2. I'm writing out our bottom equation where we separate out our I2 and I3 terms. And this is still equal to 0. Combining our I2 and I3 terms gives 6 volts minus 44.75 ohms times I2 minus 35.5 ohms times I3 equals 0. Solving this for I2 gives 6 volts minus 35.5 ohms times I3 divided by 44.75 ohms. Now what we can do is we can take this value for I2 and we can plug it into equation 1. And this is going to look a little bit messy, but it's just algebra. So all that's going to happen is we're going to say 21 volts. I'm writing out equation 1 right now. So this is equation 1. 21 volts minus 35.5 ohms multiplied by I2. So that's 6 volts minus 35.5 ohms multiplied by I3 divided by 44.75 ohms plus I3, and then I have minus 6.25 ohms multiplied by I3, and that equals 0. So now what we can do is we can explicitly multiply out each of these terms. So we get 21 volts minus 35.5 ohms times 6 volts divided by 44.75 ohms plus, because it's minus a minus, 35.5 ohms squared multiplied by I3 divided by 44.75 ohms. Then I have my minus 35.5 ohms multiplied by I3 minus 6.25 ohms multiplied by I3, and this equals 0 still. So this is still equation 1. I'm just rewriting it, simplifying and simplifying each time. Plugging this into a calculator, our first two terms combined give 16.24 volts. Our final terms, when we combine all of our I3 terms together, we get minus 13.59 ohms multiplied by I3, and that equals 0. Solving for I3 gives I3 equal to 1.19 amps. So now, by doing out this algebra, we have successfully been able to find I3, which, if you remember, is the current through the central line of our circuit. And now what we can do is we can use our knowledge of I3 in order to find I2 and I1. So looking back at our equations, our original 3 equations, which I will look at in simplified form here. So right at the center of the screen, we are looking at our 3 simplified equations. And what you can see is that the first equation has only I1 and I3 in it. So what we can do is we can take that first equation and we can solve it for I1 using our value of I3. So let's do that right now. So here we have I1, or the loop 1 voltage equation, where we now know I3, so we can solve for I1. So we have I1 is going to equal 21 volts minus 6.25 ohms multiplied by I3 divided by 35.5 ohms. And combining all of these things, we find I1 equals 0.38 amps. So now we have I3 and I1, and we can use our final equation in order to find I2. So looking back at all of our equations here, we have the equation, the second equation we could use, which has I1, which we just found, and I2. So here I have equation 2 written out with the values of I1 and I3 present. And when I solve this, I find that I2 looks like 6 volts, this should have a 0.5 in it, minus 35.5 ohms times I1 divided by 9.25 ohms. And I2 becomes negative 0.83 amps. So now we've been able to find the current through each section of our circuit individually. We found the I1, I2, and I3. Just a quick note, I want to talk about this minus sign in the I2. So I1 is positive, I3 is positive, and I2 is negative. So if we look back at our original circuit, what you will notice is that the direction that we gave current 1 was to the right in this clockwise fashion. And because when we actually did out the math, we found that I1 was positive, while we assumed I1 in this direction was positive, I1 actually flows upwards out of the battery and then to the right here. This is the actual direction of I1. Likewise, because I3 is positive, I3 actually flows downwards through this central connection. But I2 we found to be negative. We assumed that moving in the clockwise fashion here is the direction I2 was moving, but in fact, I2 is moving in the opposite direction. That is what the minus sign on I2 actually means. If we think about this logically, it makes sense if we just look at this part of the circuit. We have a 12-volt battery trying to push current down, but we have a 24-volt battery trying to push current up. So it makes sense that the current would actually flow in the direction that the larger battery was pushing, which is in this counterclockwise direction. So if we map out the way that the currents behave here, we have I2 flowing in the counterclockwise direction, we have I1 flowing in the clockwise direction, and I3 moving downward. So this is another convention that we could have chosen from the beginning. If we chose our currents to move in the way that I just drew them, we would have found all of the currents to be positive when we solved. And our equation, our current law equation, would have actually been I1 plus I2 equals I3. Because these two, I1 and I2, are moving into junction B here at the top center, and then I3 is leaving. So I3 equals I1 plus I2. So as a quick summary of what we did here, what we did was we first drew loops for each of our potential ways of moving around the circuit. So we had loop 1, which moved around like this. We had loop 2, which moved around the full circuit. And then we had loop 3, which moved around the right side of the circuit. We then used the Kirchhoff voltage law on each of these circuits individually to find an equation representing them. And we used our current sign convention to say that I1 equals I2 plus I3 based on looking at this point B. After writing down our loop equations, we simply solved the series of equations where we had 3 independent equations for I1, I2, and I3, and 3 unknowns, the 3 currents. And in the end, we were able to find the true direction of each of the currents and their true values.